Okay. Good morning, students. Welcome to Electronic Circuits Lab. This is your first experiment, common emitter amplifier. So this is a basic common emitter amplifier with a potential divider biasing. Basically, we know that we go for biasing to ensure that transistor remains in active region and the Q point is fixed. And we are using certain capacitor here. The role of coupling capacitor is to isolate the DC condition, that is the DC voltage should not flow to the input. And similarly we have output capacitance, coupling capacitance, basically to isolate the next stage, basically we want to isolate the DC condition of the first stage flowing into the second stage. And we're having an emitter bypass capacitor. The function of this capacitor is to, whenever having a AC current flowing, we should not have the drop across this RE. The AC current has to flow through this bypass capacitor to the ground. And we are going to see the design of this R1, R2, RC, RE and CC1 coupling capacitor and C. And we'll be using a BC547, which is an NPN transistor. So this is the collector terminal, this is the base terminal, and this is the emitter terminal. And I'll be setting my input to 100 millivolts peak to peak. And we're going to do a frequency analysis. So if we're going to see for various frequency, we'll be noting down the output voltage, and the input will be set at 100 millivolts. And we'll be calculating the gain, and we'll be plotting the frequency response. Start seeing the design. So before going to look at the design, we are going to assume certain things. For example, I'm going to fix my VCC is 12 volts and IC as 2 milliamps, and my beta of my transistor, which is your HFE, which is your, I'm going to assume it as 100. And these are the certain things we're going to assume because only with few parameters known, we can calculate certain unknowns. So VCE as 50% of VCC, which is 6 volts, and VC 40% of VCC, which comes to 4.8, and VE, which is 1.2. So what I'm trying to say is, this is your VCC 12 volts, and voltage drop across collector to emitter should be 6 volts, and voltage drop across the collector to the VDD, that is the voltage drop across the RC as 4.8, and voltage drop across RE as 1.2 volts. And also we're going to assume that the current which is flowing through this resistor R1 should be at least 10 times the base current. Why? Because without which, if the base during the negative off cycle, the base current will be pulled down, so that the transistor will be going to cut off. So we need to ensure that sufficient amount of base current should flow. So we're going to fix the current flowing through R1 as 10 IB and 9 IB across R2 and IB. So we're going to see the design. So since we know HFE and we know IC, we can calculate what is IB, which comes to 0.02 milliamps. And we are going to see the design of RC. So VC is equal to ICRC, that is the voltage drop across this is nothing but IC into RC. And RC can calculate, since you know VC and since you know IC, we get 2.4. Since in the lab, certain labs we can't get 2.4K, so we're going to use a 2.2K. And next we're going to see design of RE, which is VE equal to IE into RE. And we know this emitter current is almost the collector current, so we're going to assume IE as 2 milliamps. So RE is equal to, which is VE by IE, we get 600 ohms, and we're going to use 680 ohms because that is available. And design of R1 and R2, we know that the voltage drop across R2 is nothing but VR2. The voltage drop across this is VR2. VR2 is nothing but the drop across this, which is VBE plus VE, drop across this resistor. So VR2 is VBE plus VE. For a transistor, you know, the base emitter voltage is around 0.6 to 0.7, so we're going to assume it's 0.6. And drop across VE is 1.2, since we are given here, so it comes to 1.8 volts. And rest of the voltage will be dropped across the resistor R1. So VR1 is nothing but the 12 minus this 1.8, which comes to 10.2 volts. Right, now we're going to see. So the voltage across VR1 is nothing but 10 IB into R1, and we can calculate R1. We know what is the base current, so we know what is VR1. So R1 is nothing but VR1 divided by 10 into 0.02 milliamps, which comes to 47K. Similarly, we're going to calculate R2, which is VR2 by 9 IB, which is going to be coming to 10K. And mainly the bandwidth of an amplifier or frequency response of an amplifier mainly depends upon the coupling capacitor and the bypass capacitor. So when you calculate the coupling capacitor, I'm going to fix my lower cutoff frequency to be 100 Hz. And you know the input impedance of the transistor is R1 parallel to R2 into parallel to 1 plus HFE into RE. Small RE, don't confuse with the capital RE and small R. Small RE is the inbuilt emitter resistance, which comes to 25 millivolts by the emitter current, which comes to 12.5 ohms. And using R1, R2, HFE and RE, we're going to calculate RI. By using RA and FL, we're going to calculate CC1, which comes to the 1.4 microfarad, and you're going to use 1 microfarad. And design of coupling bypass capacitor, mainly we're going to assume that the reactance is 1/10 of the emitter resistance, so which comes to 68. So when you use that in calculating, C comes to around 23.4 microfarad, and which comes to 22 microfarad. So that's with the design. Now we'll just proceed with the connections and everything. And with the help of my students, we have already given the connection, whatever the diagram is, everything is being connected. So through my function generator, I'll be setting my 100 millivolts voltage, and through my CRO, I'm going to measure my output voltage and the output voltage, and I'm going to have a supply, RPS supply, which I'm going to provide. So I'll be setting this to 12 volts. And I'm giving the input to my through my function generator, and I'm measuring through my output to CRO. And you can see I've given a 100 millivolt, and now it's almost 1, 2, 3, 4, 5, 6 into 0.5, 3 volts. We have got the amplification. And what we can do is we can increase the frequency and note down the amplitude. See, the amplitude is increasing. And when we shift the frequency to kilohertz and kilohertz to megahertz, and when we go beyond 1 megahertz, the amplitude again starts decreasing. And when you go for lower frequency, again the amplitude drops. So please you can note down for every frequency, for example, say 10 hertz or 100 hertz, 1 kilohertz, you can note down the amplitude of the amplifier, output voltage, and maybe 1 kilohertz, 100 kilohertz. Then you can note down the readings, and finally till 1 megahertz you can note down the readings, and you can stop at least until 2 megahertz, the maximum frequency whatever the function generator gives me. Then you can note down the corresponding amplitude and plot the graph. So basically you're going to know what is VI, and okay, for every frequency you're going to note down the V0. So say starting from 10 hertz goes on till 1 megahertz, note down the corresponding voltage, and find out what is V0 by VI. Then finally you can note down what is gain, which is 20 log V0 by VI, and finally you can plot gain versus the frequency in the semi-log graph, and certainly you get the graph like this. And once you have done, you can go for a -3 dB cutoff and find out what is FL and what is FH, and find out the bandwidth, which is FH minus FL. So certainly the amplifier will amplify only if the design is perfect, otherwise the amplification will fail since the Q point will shift. So thank you. This is the end of the first experiment. The next experiment is nothing but you're going to go for a multi-stage amplifier. You're going to duplicate another stage, and we are going to again do the frequency response. Thank you.